Okay, is there someone from the Hinckley Institute here? Okay, so someone from the Hinckley Institute is supposed to come and talk for 5 minutes about some form of internship. But if not, then that's okay. Oh, I've got some volume on. Um, yeah, yes, okay. So then let's get started. So today this is the last lecture on a long section on how to measure similarity and how to compute with these efficiently. So be on distances for distributions like probability distributions. Before we get into that, just review where we are. There are a couple of things coming up. We're about to start the clustering section of the semester. The locality sensitive hashing or the LSH homework is due. Are there any questions left on that homework? Has that been pretty straightforward? Once you figure out what I was actually asking you to do. Okay, so then the other thing coming up is the data collection report. This is not until almost 2 weeks, but we'll only have one more class between now and when this is due. If you are interested in data having to do with healthcare or kind of or medicine, I'm going to have someone come and talk at the beginning of the lecture on next week, Wednesday, about that kind of a center on campus that tries to organize and prepare and make available a bunch of this sort of data, just to talk about some other things. So the projects, you had your project proposals, you've had your project teams, that should all be good. The data collection report is the next milestone in here. You decide you kind of aren't liking the direction your project is going, it's always okay to kind of shift topics a little bit. So it's good to keep in mind. So even though I'm having someone come out on Wednesday and the data collection report is due a week later, the things are flexible if you want to change things, but most people will stay on the same topic. So the data collection report. So it's kind of, so each group together should turn in one page, right? So I believe it should be set up on Canvas now. So it's a group thing and hopefully this will work out. So the group together will turn in just one page, one document. And it's kind of it's kind of a checkpoint, so you're still working on the project, even if you haven't learned all the kind of techniques you'll need yet. And so just a report on how you obtain the data, where is it from? Did you just download it? Did you have to scrape it? How large is your data? Just give a sense. It's important, one, for you to think about how large the data is. If you choose it so it's too small, you may not be able to reliably find any signal in it because it's just too sparse for the sort of patterns or structure you're looking for. If it's too big, you may need to start thinking about, can I store it? Can I run the sort of algorithms I want to on this, or will it take too long to do that? What format are you storing your data in? And so I'm not thinking just the file format, but like we've talked about things like sets and vectors. We'll talk about representing things as probability distributions now. These are kind of the sort of questions to run any of the algorithms we'll use in class. You'll have to somehow convert it into this abstract representation. It's possible if you just downloaded something off of Kaggle or something, it'll already be nicely formatted. But if you work with something more from some area of your personal interest, it probably won't be, right? So you want to think about how are you representing it? How are you thinking of measuring the distance between kind of the data elements? That's really what I'm asking here. Not how do you how do you model the distance, and two, kind of like what is the distance measure you're planning to use? Okay, and then did you need to clean it? Did you need to compress it in some way? Did you need to kind of like do some sort of processing with it? If you are going to do that, I want you to at least try and make a first pass on this first. And if you find you try and do it by Wednesday and you're like, I'm not sure I did this the right way, well, then that's a great question to come ask me. Okay. But I want you to force yourselves to start thinking about these questions. And then the last one is the one that kind of trips up people the most. How would you try and simulate the data? This goes back to the second lecture of the class when I said for like anomaly detections, in order to anomaly detection, you need to be able to think, okay, what is the baseline distribution this data probably came from? And then is mine somehow different from that distribution? That would be something anomalous or interesting. So that's the sort of thing I want you to think about. If you were to generate synthetic data, say your data set is pretty small. You found it's really interesting. It's about some topic you really care about, but you only have like 20 different observations. Well, okay, so let's say I want to assume I could collect more data. I wanted, and I'm not finding the patterns. I'd wanted, could I simulate a bunch more data so that I did have more data at a larger scale? How would I do that simulation so then I could try and run this in case I'm able to gather more data later? So that's kind of an important question to ask in a lot of topics in data mining. It kind of gives you a baseline and it gives you a way to kind of see what happens with scale with data of similar somehow structure to what you think it might have. Okay, any kind of questions about this? Okay. Yep. Yeah, look, so how it's going to be graded is mostly the TA will go through and look to see if you answered all these questions. So if you can write down all these questions and write answers to them, that would make it easy, right? If you don't know how to answer the question, you can write down, we've thought about this and here's what we're thinking, but we're not sure how to answer it. That would be okay also, right? But I'm kind of trying to make sure you're working on the projects throughout the semester, not this at the end. Is that getting what you're asking, or is yours? I want you to think about how you would simulate the data. Maybe there's not a good answer, and there's a reason for that. Okay, maybe you're not sure, but you have an idea, and maybe you'll try that out. Maybe you'll try and simulate the data in a way you're not sure will work, and then you look at your real data and you've tried. Part of your project is comparing, did it look like how I thought simulated data would look like? Okay, and that might end up being part of your project. Okay, but it's a really, it kind of, if you have a good way to simulate it, means you have like a model of what you think the world looks like, a physical model. And if your data matches that, then that's a good way of somehow trying to, some way of validating that physical way of thinking about how the world works. So that's I want you to try and answer that question. Look, you're not going to be graded on, oh, this is totally the wrong way to simulate it. But if you think about it, you'd like more feedback on that, you should come and talk to me. But the point is for you to try to answer all these questions. Is it just fake data that you generate? That's not how I like to call it, but that's a reasonable way of thinking about fake data that you generate. Yes. Yeah. I don't like calling it fake data because it implies, but it can still be useful, right? It can be fake, but still useful for. So like it can tell you, let's say you're pretty sure it has this certain pattern, and you generate fake data, and you can find that pattern in the fake data, but not in your data, or the patterns are different in yours. Well, maybe that means you don't have enough data for this to be reliable. But you want to be as realistic as possible, right? Yeah, but it's not observed or collected the same way some of the other data is. It could be the data you're working with is the output of someone else's simulation, right? There's a big field of scientific simulations for, trying to predict what the weather is, how they predict the weather. They have a bunch of different models. They predict how the model of the pressure and the moisture in different parts of the earth will go forward, and they simulate it. And then people look at the simulations and trying to make a forecast for the weather. So their data is just the simulations, right? So I don't want to call it fake data. It doesn't need to be fake. It can be very real and useful, but it's not necessarily kind of a direct observation. Okay, any other questions? Okay, great. Well, you can ask me again on Wednesday or sometime before then. One more thing. Probably this Thursday, I may not be able to hold office hours. I'm on some like Zoom call with one of the funding agencies. If you knock on my door, I may try and answer. I thought it might get canceled. But looks like it's not going to be canceled, which is probably good news. So if you really have a question, I'll try and answer it, but I may not be able to, depending on what's happening in the meeting. Okay. Okay. So distances for distributions. Okay. So far we've talked about kind of our abstract representation. Mostly two things. One was that our data point was going to be, we converted text through k-grams and stuff into a set. And two, where we converted a data point into a vector. And these were kind of the two ways we thought about this before. And so there's another important category that we had not talked about really much in this. I mentioned a couple things in this class, but this is a very common thing. And the third thing, so today, where a data point is going to be a distribution, okay? And this can mean a couple of different things. And I mean like a probability distribution. And so there are things we could have used before for this, but they didn't quite respect the probabilistic nature or something, or the kind of the spatial nature of this. Well, let me start by reviewing a couple of things we've talked about before. The first is when we have a discrete distribution. Okay, we talked about when we have like m possible outcomes. So think of a discrete random variable. The outcome of a discrete random variable is m possible outcomes. Okay, and so these could be, say, m equals 100,000 words in English. Okay, so when we did this, when we looked at things like this bag of words model, or the pairwise or the positive pairwise mutual information vectors we use to derive these word vector embeddings, it was kind of based on this idea that there are 100,000 possible words. We kept track of the distribution of each of these. It could also be something like So that in the state of Utah, there are 29 different counties. So if I'm looking at votes or lightning strikes or kind of where there was like a car accident or like a birth, these happen in one of these 29 counties. Okay, and so I want to understand the distribution over those counties, right? And so there are other details of location, but maybe for privacy, I've rounded it to one of the counties. I just record that information. And it can only occur if it happens in Utah, it can only occur in one of those 29 possible states. Okay, so the typical way of dealing with this is, again, to represent as a vector in Rm, but this is not the fully correct answer. I mean, I could use as a vector in Rm, I could use Euclidean distance between these things, and we'll kind of come back to this. But this kind of is too flexible. This is too flexible, because if it's a probability distribution, it shouldn't be all vectors in Rm. Okay, so what we typically do instead is we say that for discrete probability distribution with m states, okay, I represent as a vector in Rm, but I want to restrict this. I want that Vj is equal to the probability in state kind of j in the set of these m states. Okay, so I want that the jth entry in the vector to represent the probability being in the m states. Okay, so when I do this, I know that the properties of a probability are that Vj then must be in 0 and 1, right? Any probability must have a value between 0 and 1. It can't be negative, importantly. And that the sum over all j equals 1 to m of these Vj states must be exactly equal to 1, the law of total probability. So it must be each event must be in exactly one of these states, and if I add up the probabilities, they must equal to 1. Okay, so what this does is it gives me the space that I call triangle m minus 1, and I'll kind of explain why we write it this way. Okay, so this is going to be equal the set of vectors in Rm such that xj is greater than 0. Really, unit force is between 0 and 1, but I just need greater or equal than 0. And the sum of xj equals 1 to m of xj, which is going to be equal, because they're all greater or equal than 0, the L1 norm is equal to 1. Okay, so I have these properties. So if I have data that's in a probability distribution, it's this specific subset of Rm. Okay, and there's a nice geometric way of thinking about this. So I can think of, okay, these three-dimensional space, and I know that there are going to be these three possible values. This is a case where I'm in R3, and I'm going to describe the state triangle 2. Okay, I know that these three possible states and 0, 0, 1, okay, that I know those three states are all valid, where I have the first one on right here along the first axis. That means it's always in the first state. The first state is always true. This is the second state is always true, the never states other exist. And this is the third state is always true and never the other states. But it's really going to be the kind of the convex combination of these. So I could look along this line here. And so this, for instance, if I look at this point that's halfway between these two states, this is 1/2, 1/2, 0. Okay, so it's 1/2 the probability of the first state, 1/2 the probability of the second state, and 0 probability in the third state. And kind of if I fill in this triangle here, it's all possible states in here. It's all convex combinations of these. Okay, let me try and draw this a bit better here. Right, so I have these three states, and I'm going to call this one E1, E2. This is how they're, and this is E3. And so this triangle 2 is all possible regions in here, which is the convex combinations of these three states. Okay, and in general, if there are M states, it's the convex combination of those M states. And so I call this triangle 2 because it's a space that looks like a triangle. It's always going to be an equilateral triangle. This is called the 2 simplex sometimes called the 2 simplex. The 3 simplex will be like a tetrahedron, and a 4 simplex is kind of the next most generalization of this. But I can always define it by defining the M kind of corners and then looking at the convex hull of those spaces. Okay, and so this turns out, because it's a convex is a subset of linear combinations. So this is a linear subspace. So it looks like a linear subspace, but M-1 dimensions. Okay, yeah.
So what does this triangle actually represent?
This is the space of all probability distributions represented as a vector. Discrete probability distributions with M states. I've taken away 1 degree of freedom because I know the sum of them has to be equal to 1. So that removes a degree of freedom, and I go from M-dimensional to M-1 dimension. I've lost 1 dimension. Still plenty of dimensions out there. If M is 29 or 100,000, right? Okay, and so this is the space of these discrete probability distributions. And then I can define distances on this space. Okay, and this is what you want to use for discrete probability distributions. Okay, you want to start with this kind of your data is represented in this way, which is a slight restriction of kind of Euclidean space. Now I could say for V and U as 2 elements, I could compute the distance V between V and U is equal to just the Euclidean distance between V and U. I could do that, right? I could have 2 points here, V and U, and I can just use the straight line distance between them. This would be a perfectly valid distance, but this is not commonly used here. It doesn't say much about the probability. Okay, so there are some other more common things people use. And let me just write these down. Okay, so for data as say A and B in M-1, okay, then common distances are so one is the Kullback-Leibler distance, or Kullback-Leibler divergence, which is written this way. And this is, once I write this down, it'll look a little bit maybe strange if you haven't seen this before. That's the natural log of AJ BJ. Okay, so this is not symmetric. Okay, the distance between A and B is in general not going to be the same as distance from B to A, so it's not going to be a metric. But this tells me the amount. It's an information theory derived thing that comes up a lot in a lot of derivations of of what is the right way to measure distance between these things. And it measures if I know something about probability distribution A, and I have that, say, on one side of a channel, and someone else says, well, your starting point is A, but I really have distribution B. I want to convey information relative to A. How much change do I have to convey to tell you my distribution B? And so this is kind of an information theoretic property. How much information do you have to describe between A and B from these? And so it's should look something like entropy. Okay, but this is a very common distance. So note that if A or B is 0, this does not make AJ or BJ is 0. This does not make sense. So you can't have things have a probability 0. When you use this, often you kind of round them up to a very small value. Okay, so this is one common distance. Another one is the Hellinger distance, which I'll just write down, is going to be, yes, 1 over square root 2. They normalize it typically, times j equals 1 up to m of aj square root of this minus the square root of bj squared, all under a square root. Okay, this looks kind of weird, but this Hellinger distance is a pretty common distance used as well. It is a metric now on this space. So if you think of that, your space, this is just triangle 1 here. Okay, what I can do is I'm basically lifting it up to this wedge. When I take the square roots, I'm kind of thinking of a point here, and I convert it up to, this is like square root of A. I'm kind of lifting it up there, and then I'm doing Euclidean distance between two of these objects. Okay, so it once you map it up, it's like it inherits the metric properties from up there. And so you can always lift it up to this wedge that looks like the hypersphere. Okay, and then probably the most powerful one is called the total variation distance. Okay, so I'll first write down the formal complicated form, and then I'll write down this simplified form. Okay, it's the max of all subsets of the possible variables times j equals 1 of aj minus or j in this subset. So of all so j in S bj. So I just look at the difference, one direction difference from A to B. So all the ones where A is bigger than B, I subtract A and B. Okay, this is exactly equals to A minus B with the L1 distance. So this total variation distance, the TV distance, is kind of the most powerful distance. It's the most fine-grained distance possible. Okay. So often, if you get a bound on total variation distance, you get bounds on all the other distances. So it's a very powerful thing. Okay, so these are kind of things you do on discrete probability distributions. Okay. Okay. Just want to mention these things so you're aware of them. They come up in a lot of different work in data mining and data analysis. Okay. And I kind of want to mention them because the next thing we want to talk about are so what if the distribution, okay, that we're talking about mu is going to be a continuous probability distribution. So think of, there's some, continuous probability distribution where I have some function value mu, and if I integrate mu dx, it's going to be equal to 1, right? If you remember calculus, continuous probability distribution is continuous function integrates to 1. Or I think about, I have a sample P from you. So I've got a bunch of points I've sampled. Okay, so now this is one object, right? The object is the distribution. I have an algorithm, and I've tried out a bunch of different algorithms, and I ran an algorithm, and it was a randomized algorithm. So the output had a bunch of different, say, runtimes, or a bunch of different estimates of some quantity. And I ran it 7 times, and I got those 7 red points for the runtime or the value I estimate. Okay, and now I ran, this is for kind of algo number 1, gives me P, and then maybe Q, I'm going to run algo number 2, and I'm going to get some different values here. Okay, so Q and P, they have different outputs, and there's different runs of the algorithm. How do I compare these algorithms? Which one was better? Okay, how do I compare these things? Okay, or I'm measuring the rainfall. Okay, so I could just measure the total rainfall between cities, but maybe someplace like Tucson has a surprisingly large amount of rainfall, but it comes all in these kind of monsoons. Whereas another place has steady drip, drip, drip over the whole year. They might have the same total rainfall, but the distribution and the patterns of it is very different, right? These are continuous values, and I observe it over different days, right? And so I get different amounts. And Tucson is probably bimodal, usually absolutely no rain, and then there's these monsoons. And in Seattle, it's this drip, drip, drip all the time, right? So how do I compare these continuous distributions to each other? Okay, and in your homework, we're talking about the Kolmogorov, how do I spell this? Kolmogorov Smirnov. Okay, they don't. So it was Kolmogorov who really invented it, but he invented a lot of stuff, or maybe other people in his family. So Smirnov helped build some statistics on it. So you put his name on so you know what you're talking about. Okay, the KS distance, and then I can call it the KS distance. Okay, now I'm going to have 2 probability distributions. Okay, we'll think of here now 2 probability distributions that integrate to 1. Okay, and so then I convert them into the CDF. Okay, so the CDF is kind of is integrating these things, right? So it's the integral, it's the probability, the CDF of the purple one is the probability of that the value is this or smaller. So it's between 0 and 1, and I have the blue distribution. Okay, and they both end at 1. Okay, and now I want to say that so I have the CDF of P, for the blue is the distribution P, and the purple is the CDF of Q, where Q is the purple distribution here. Okay, and so then the Kolmogorov-Smirnov distance between P and Q, these could be samples, and then these are step functions and so forth. So, but let me just use P and Q. Okay, this is going to be equal to the max of all Z in the real values, where if I look at the CDF of P of evaluated at Z minus the CDF of Q divided at Z, and the absolute value of this difference. Okay, so if the biggest difference between these is right here, this is the value Z, or maybe this over here is, I have to look at all the possible Z's and find the one which maximizes this, okay? And so for the last question in your homework, I asked you to calculate the difference between pairwise distances between these high dimensional vectors and trying to say which one was randomly generated, which one is example from these word vector embeddings. Okay, and this is the distance between them. That's the maximum value between these two. Okay, and this is a metric between these distributions. Okay, so I could have used a discrete distribution instead, and if this was measuring the rainfall, I could count, okay, how many inches fell in each day. But if I have if I have a very precise measurement, if it's kind of 0.321 inches versus 0.323 inches. Okay, if I have a discrete probability distribution, these are totally different, and I don't notice that these are similar to each other. Okay, but in here, I know that these are going to be 2 points which are going to be very close to each other. So as I'm sweeping the cumulative density function, I always include the first one if I include the second one, right? And something far away doesn't get included until later. So I'm somehow incorporating and retaining the spatial coherence between these, just in one dimension. Okay, and so this is a pretty easy to solve by sweeping over these, at least with discrete points, and keeping track of the CDFs and keeping the maximum difference here. Okay, okay, and it's important because it captures kind of whatever the distribution was measuring. It's some continuous thing where the similarity between 2 points mattered somehow. Or at least in this case, I just needed the ordering between the 2 points. I don't care about similarity, just the ordering between the 2 points. Okay, make sense? Okay, if your data is one-dimensional distributions, this is a really nice, easy one to use. Okay, okay. So these were the two warm-up things we want to do. What I actually want to talk to you about are these 2 other measures where the inputs are continuous distribution on RD. So this is kind of combining together these sets and these vectors. Okay, so I'm going to have mu, I'll call it mu p, and nu, which is another Greek letter you probably aren't used to using. It looks like a V. Nu q, and I'm going to typically think of drawing p will be drawn from mu p, and q will be drawn from what's that? Nu q. Okay, and in this case, p and q will be subsets of RD for some multidimensional setting, and I will assume for now that the size of P equals the size of Q equals N. Okay, so we just have N points from each. It doesn't have to be the same, but this will just kind of simplify some of the discussion. Okay, now I want to have these 2 point sets, P and Q. Think of there's a uniform measure on them, but they're representing these continuous distributions in multidimensional space. Okay, so I'm looking at students from the class, I'm measuring their height and their weight, or I'm taking words and I'm embedding them into a 300-dimensional space. Okay, and I have 2 languages. I have English and I have Spanish, and I've taken words from both and embedded them into 300-dimensional space. Do they have similar kind of distributions to each other? Turns out, surprisingly, the answer is yes. There's a lot of shared structure between how these languages get embedded. Okay, and more so between English and Spanish than between English and Japanese, as it turns out. Okay, so you can do this by measuring the similar distributions of these kind of discrete high-dimensional points, but I need to be able to compare where the inputs are point sets or they're representing continuous distributions. I can often think of them as samples from these distributions. Okay. Okay, and so far we can't really use the discrete setting because they could be anywhere. I don't have a fixed precision on these things, and I want to measure spatial coherence. There are kind of ways to generalize Kolmogorov-Smirnov, but they're not the most popular approaches. And so let me tell you about the two most popular approaches, and I'll just write them down first. The first one is called the Wasserstein distances. Also, there are versions called Earth movers distance, or optimal transport. Okay, and the other class is called, I call this the kernel distance. It's more popularly called maximum mean discrepancy. So, which people just call MMD. Okay, but and so one reason I haven't lectured on this in Daemine before, but is that these have become kind of, there's a lot of active work on this. These are used quite widely, and I don't think they're taught anywhere else in any of the classes we teach. But I know probably a quarter of the faculty are working on research projects that use these distances somehow, right? They're used in a lot of innovations in understanding kind of how well does outputs of machine learning and stuff work, right? Or how do outputs of simulations, which are probabilistic, work, right? These are very powerful, important sort of notions. Okay, who's heard of maybe one of these before? Maybe it's, and this is kind of pretty new for the rest of these ideas. Okay, cool. Okay, so we'll start with the Wasserstein, which is probably the more powerful, probably a bit more popular, but I'll say it's harder to work with. Okay, the kernel distance will turn out to be a lot easier and more efficient to work with, and we'll be able to map it back to a setting where it basically acts like Euclidean distance. So we'll be able to use the kernel distance in a lot of the rest things we do in the semester, where we assume things are linear or Euclidean, but now can be about distribution. Okay, cool. So the Wasserstein distance, we're going to again assume the input P and Q are both subsets of RD. Okay, the size of P equals the size of Q equals N. This doesn't need to be true, but kind of will simplify our discussions a fair bit. We'll assume they're points drawn from some underlying kind of these distributions. Okay, and this is called the Wasserstein is often called the optimal transport distance because in order to compute it or to define it, I need to define a transportation. So my input is again going to be something like a set P, and then another set Q. Do I have the same number of points? One more over here. Okay, and so I need to define somehow a transportation plan between this transportation plan gamma between P and Q. We'll say gamma is going to be an element of the space of all transportation plans, which I will, between P and Q, which I'll define. And that will be something like a matching in between these point sets. Okay, so I'm going to match every point from P to a point of Q. Okay, this matching will define this gamma. Okay, and I has to be, if I have equal size point sets, this will have to be a perfect matching and a perfect, so bipartite matching, each point from P maps to exactly one point from Q and vice versa. I can't have one point from P matched to 2 points of Q or something like that. And everything needs to be paired. Okay? And so this is sometimes called the Earth movers distance. Okay, and the idea is that there's basically these, well, let's start with the, one set of the points are these mounds of dirt, right? These big holes that some gophers have left, right? And then on the other side, there are these holes in the ground where I think this dirt may have come from, and it may have been distributed in some continuous way, right? And I want to somehow move all the dirt so that it's flat, right? So I want it to become flat. And so I want to say, well, what's the least amount of work I have to do? And so I pay a distance to move earth. So I want to find the minimum cost of the movement of the earth. And this is, when I set it up that way, it's called the earth mover's distance. Yeah.
It's gonna ask.
Yeah, okay, so there are generalizations of this and so forth, but in general, we'll talk about this for probability distribution, so they both integrate to one. Now, maybe I've sampled different number of points, then I have a different, each point has weighted based on 1 over the number of points in the sample, and I need to distribute the weights so it balances. Okay, so I can still think about it, I can have a bigger pile and a smaller hole, but I can only move the amount of dirt to fill the hole. The rest of the dirt has to go someplace else. So it does generalize, but the notion of what is a transportation plan that's valid is a little bit more complicated. So I'm going to skip it in today's lecture. But this does naturally generalize to different weights and all sorts of stuff. Okay. This was also used in the time of like Napoleon, apparently, and trying to figure out the movement of troops. He's like, okay, I have a different strategy for the battle plan. I have my troops here and I want to move them over here, or I have a bunch of supplies and I need to get the supplies like wheat out to my troops so they have food to eat. How do I distribute it with the least cost? I don't want to move too much wheat to these troops. They don't need it, and not enough to someone over there. How do I minimize the cost of supplying my troops, which are scattered over the battlefield? Okay, this is trying to find the best transportation plan. Okay, and so this version would be, so this earth mover's distance would be a special case of this, where I want to take the sum over all the PQ, which is in my transportation plan, gamma, okay, and I'm going to add up the distance between this P and Q, okay? And then I usually take the average. So let's say they have the same size, so I average over 1 over P. It's the same as 1 over Q, okay? And then I want to minimize gamma over all the valid transportation plans, which is these matching. So I want to find the matching which minimizes this. This would be called the earth mover distance here. Okay, this is a special case. Let me write the more general case. I'll write it in a couple of generalizations. The kind of the Wasserstein and WS. So S is going to be a parameter, and so look familiar. Between P and Q is going to be the minimum over all the valid transportation plans, P and Q. Okay, 1 over the sides of P, sum over P and Q in the plan, P minus Q. The distance from P to Q, this is and raised to the power S, and I take this all, and then the average, now I'm taking to the power 1 over S. All right, so if S was equal to 1, this is equal to W1, the Wasserstein 1 distance here. So the earth mover distance is Wasserstein 1, and the Wasserstein 1 and 2 are pretty common, right? So this is a metric for S, just like the LP distances, for S in 1 up to infinity, and then you can define a W infinity version where you have a max instead of some averaging. Okay. Okay, so this is the Wasserstein distance. The Wasserstein 2, I'm paying the squared distance instead of just the distance. What this does is it really penalizes far away matchings because I have to take that distance, then I have to square it, right? So think of if you're moving wheat on the battlefield, I guess wheat, maybe apples is a better example. The apples might get rotten by the end of the trip. Then it's better to move them closer. So I really want to penalize really far distances. And the Wasserstein 2 does that better. Also, computationally, there's some nice, it's a little bit easier to compute. I can also describe kind of a more general form, Wasserstein S, between probability distributions, mu and nu, as now I need to write the infimum because there may not be a well-defined minimum, or so now I would need to define transportation plans between these probability distributions, and then this is the expected value over P and Q in my drawn, I guess, drawn, then the transportation plan is a distribution over pairings, and I draw a random P and Q from that, and I can have for any distance P and Q to the power S, all to the power 1 minus S, right? And so again, for any distance, which is the base distance, is a metric, and I use S in this range, then this is again going to be a metric between these. So it's a kind of a fairly general notion. This can be over any sort of metric space. It doesn't need to be RD. There's some very deep mathematics on kind of the generalizations of these things. So it's a very powerful general. Okay. It's often called the optimal transport because to calculate it, I have to optimize this transportation plan. Okay. So I'm not gonna, so in order to calculate it, even in the case where P is equal to Q and there's point sets, I have to compute this min cost matching, right? This transportation plan, which is, it's so not trivial. Okay, so if you use this, you'll probably use like a library, right? Let me just say computation on W1 and so W2. You kind of need to find the R min of gamma in the space of all the transportation plans, right? So you have to find this optimal transport between the point sets. Okay, I can't just like Euclidean distance between two vectors. I have the formula I wrote down, right? There's no longer just a formula. I need to do computation to solve some optimization problem just to compute the distance once. Okay. Okay, so it's a little bit more cumbersome to work with. There are some algorithms for W1 and W2, but they take something like n cubed log n time. Okay, so usually you'd be given the pair of the input as actually the all pairs distance, right? So the input might be n squared size, right? So where you would pre-compute you might say, I'm going to have to compute all the distances between 2 points in P and Q. So you might think of that as the input, and then it doesn't look so bad. But if you want to compute this on like, I have 100,000 points I've embedded, n cubed is looking pretty bad, right? So this is kind of kind of slow to work with. I will mention there is a approximate W2, and this is well known, called the Sinkhorn algorithm. Say it's one of the cooler names in the space of algorithms. And what this does is it adds kind of some entropy regularization. So it basically penalizes really far distances in some way, but the advantage is that it becomes a convex optimization. Okay, and then I can solve it for an epsilon approximation. So I'm off by a 1 plus epsilon factor in time 1 over epsilon, or it's, I think, 1 over epsilon n squared times some log factor. Okay, so I've basically gotten it down to roughly n squared if this is a small factor in the approximation. Okay, so this Sinkhorn algorithm is the popular way to calculate it for W2, and this does not depend on the dimensionality. My input, if I think of it as the n squared pairs of distances, then I don't care what the dimension is, I just work on those distances. So it doesn't depend on dimension, so I can use it in my 300 or 100,000 dimensional space, as long as I have all the distances, but it's still kind of n squared. Okay, this kind of is the cost of using this, yeah.
For the epsilon?
There's some log factor. I forget if it's n or 1 over epsilon. Let's say log n. Yeah.
So the pros of this,
yeah, so this is kind of, so we'll talk about this kernel distance next. And this kind of things that are kind of far away, it can kind of ignore them. It doesn't matter how far away they are. They're just saying, okay, those are far. I don't, and it's also more fine. I actually get out of it when I calculate it. I get this transportation plan, right? So I know something about, okay, I assume there was some movement from here to here, right? What was that movement? Where is the movement happening? I can analyze it. There's more structure going on. I can't miss anything. Everything needs to be paired. So it's kind of a more powerful distance. It tends to, like, they've used these in like GANs, these generative adversarial networks, where you want to learn a distribution of your data, and so you can generate from it. So I need to be able to learn a distribution of all the input space in some sort of embedding space. One of the issues is that you can learn something that everything looks like something from your input, but there might be a whole part of your input space that you miss, right? And so they have, one of the most powerful things they figured out is that if you try and show that there's a Wasserstein GAN where you try and ensure that the representation of the distribution in the parameter space matches the data and the guessed model distribution is close under Wasserstein, then you don't miss any of the modes of types of faces you're trying to generate or something. Ensures everything is taken care of, but there's something that represents each of the data points. They tried to do this with the kernel distance as well, and it doesn't quite work as well. It can miss certain modes. It's still better than not any regularization, and it's a little bit faster, easier to optimize, but this Wasserstein version works better. Okay, it's a really powerful distance that makes sure you take care of everything, like no point left behind sort of distance. Okay. All right, okay, how to speed this up? I think, is there a faster way to do this? It's still kind of an active research area. In fact, I'm actively working on some questions in certain settings. Can we get this so it's near linear runtime instead? Right? There's some cases where we hope we can do something. Okay. Okay, good. So let's talk about this other measure called the kernel distance. Okay, and who's heard of the kernel trick in machine learning? Okay, so this kernel distance will be kind of based on the kernel trick. It uses a lot of similar ideas going on. This came afterwards. Thought of it, how do we think about distributions, distances between them? But it kind of, I think, hopefully it'll give another way to understand what the kernel trick is doing if you haven't seen this before, which before deep learning was kind of the coolest thing in machine learning. Now there's still arguments why kernel methods explain a lot what's going on, but they're not the coolest kind of bird in the hen house now, or some analogy. Okay. Okay, and this will also be maximum mean discrepancy. And hopefully by the end of the lecture, I will kind of give some sense of where that name comes from. But I think the kernel name is pretty obvious, which is okay. So I need some notion of similarity between 2 points P and Q in RD. Okay, and so a common way to do a notion of similarity would be a kernel. And I'm thinking like a Gaussian kernel. Right, so examples like a Gaussian would be K of PQ equals the distance between P and Q squared. Okay, so if I were actually writing a Gaussian down, I would need to normalize it in front, and I'd probably divide by the standard deviation and maybe 2, but here I just need this form. Okay. This is the canonical example of a kernel. It looks like the normal distribution between P, and then the similarity for Q is going to be highest around P. So this is K of P Q, right? This is depending on where the value Q is here. That height gives pretty poor Gaussian, but looks kind of like that. Right, and the way I've set this up is so that the maximum value is 1 and the smallest value is 0. Okay, so I want, okay, but there are lots of notions of kernels that I can choose. There's lots of modeling. There's a Laplace kernel, which is okay, where I don't square it. This would be a Laplacian kernel. It looks like this one, but it's pointier, and the tails are a bit heavier as well. Okay. There's the triangle kernel, which is we talked about this in class as well. The triangle similarity, max with 0 and 1 minus P minus Q. Okay. This one looks like this, right? It's just straight down and then 0. Okay, and then, but in general, I can write that kind of a general Gaussian. I can write that K P Q equals okay, so I could use basically any distance, any metric distance inside of it, and a negative of that inside of an exponential. And if this is a metric, then this will have perfectly nice properties. So I can basically use any distance I want inside. Okay, or I don't even need to square it. I could do the unsquared version. Okay, so this kind of, there's a lot of properties of kernels. We're going to want 2 properties. Property P1, that K, AI trying to jump in here. It's as excited as I am about these kernels. Okay, and that the output value is between 0 and 1. And how I've written all of these satisfies it. Okay, we're going to say the output is, you can get away with it's between 0 and some other fixed value, but we'll say 0 and 1. And then property P2 okay, that must be a shorthand to
delete what's inside there. Okay, property P2 is that K is positive. So positive definite. Okay, so a kernel being positive definite means that the gram matrix it generates is positive definite. So we can say a gram matrix G is going to be in our n by n, and where G of ij is going to be the kernel of xi xj, and we're going to say that G has all real and positive, so eigen values. Okay, so if this is true for any x, so for any point set x, I take any point set and I create of size n, I create n by n matrix where the entry gij in the matrix is defined by the kernel between xi and xj. So I write this down to big N by N matrix. If that is a positive definite matrix for any input x, then the kernel is positive definite. And again, positive definite matrix, if you don't remember this, it means I take the eigen decomposition, I look at the eigenvalues, they're all real, they're n real and positive eigenvalues. That's positive definite. So positive definite kernels, it's a really nice property. It's the first time if this is the first time you're seeing it, you probably don't believe it's true. It is true that you can do this. Everything, the Gaussian, the Laplace, the generalized Gaussian, those are all positive definite kernels. The triangle kernel is not. Okay, but it's something about smoothness and kind of going off to infinity. You don't need to have those properties, as it turns out, but you can. There's a large class of positive definite kernels. These are, again, the most common forms. Okay, so these are going to be the two properties we're going to talk about for kernels so today. And basically, if I'm going to define a distance between point sets with kernels, and if I use a positive definite kernel, it's going to be a metric. Okay, so more or less on Euclidean point sets. There are some. If I use the general version, there are some exceptions to the rules, but not too much. Okay, so now I want to use this property. So an analogy, okay? You may not think you get a lot of analogies in a data mining class, but it's going to be a mathematical analogy. Okay, that if I look at the squared Euclidean distance between P and Q, okay, this will be I can write this down, I can expand this, minus 2 times the inner product, this is the dot product between P and Q. Okay. So you've probably seen this expression before with just two values, P and Q, but it works with a Euclidean norm as well. Right? If I just do P minus Q squared, where those are scalars, I get that's equal to P squared plus Q squared minus 2PQ. Right? And this is the generalization of this. And in fact, I can write this as P dot P plus Q dot Q, because that's equal to the squared norm minus 2PQ. Okay? So I can write this way. And the key insight is I want to use KPQ as a similarity, so as P dot Q. Okay, I'm going to use it in place here. All right, so I'm going to say that I'm going to find the kernel distance between P and Q is going to be K of PP plus K of QQ minus 2K of PQ square root. Okay, and if K is a positive definite kernel, this is a metric on kind of Euclidean points P and Q. Okay, so this is good, but I haven't gotten this to distributions yet. So I need to now define this for distributions. So I need to define a generalization of a kernel for these distributions. To do that, I do, I'm going to basically take the average similarity. Okay, so to define a similarity between point sets, I now look at the average pairwise similarity. I look at all pairs of points in P and Q, and I compute this. Okay, so I don't need a matching anymore. I'm just gonna average these things out. Okay. Okay, and then I can write down the kernel distance, dk between P and Q is going to be P, so I'm measuring the similarity with itself, K, Q, Q minus 2K, P, Q. Okay, and if the kernel is a positive definite kernel, and these are point sets in Euclidean point sets in RD, then this is a metric. So I'm subtracting something here, but just like with the norm property, the sum of these values will always be bigger than 2 times the inner product. Okay. The positive definiteness, you can show that this works out. And this has to do with all the eigenvalues being positive of any sort of gram matrix. Okay, and I can generalize this by making this an expected value over 2 distributions to get a version of this defined for continuous distributions as well. Right. So, so this is a distance between probability distributions. Okay, and computation, it seems a little bit nicer. It's a little bit straightforward. I have to compute this all pairs property. But if I had all the distances, I just take e to the negative the distance squared inside of here and add these things. And then I get a nice metric between these probability distributions. Okay, I have a few minutes left. Let me talk about the Euclidean-like properties of this for a few minutes. So it's more straightforward to calculate, but it also has these Euclidean-like properties. Okay, and I want to start with if I have X equals P union Q, then I want to think of the gram matrix G of X, where G of IJ equals xi, xj, and xi or xj could be points from P or Q. Okay, to calculate the distance, I somehow need to look at these kernel values. If I compute this gram matrix, it has in it all pairs of the distances, and so this will contain all the information I need. But it turns out that once I've written this gram matrix, this is an R kind of, I guess, 2n by 2n at this point, because P and Q both had endpoints in them. In this space, it's going to act like it's linear. So I can then do the eigen decomposition. Missed some letters there. Decomposition of G, and the output of this will be a set of, and we'll talk about this a little bit later in eigen decompositions, review them later in class, but we're not going to have time to do that today. These vectors and values, and now we want to look at these eigenvectors. U equals U1, U2 up to U2n. And so I can form, and these form a basis, and I can project all of X, P union Q, into the basis defined by U. Okay, and if you're rusty on the linear algebra, don't worry about it. But then in this basis, the Euclidean distance is equal to the kernel distance. So if I have 2 points in the basis and I project them onto here and I calculate the Euclidean distance inside of, once I project it into this basis defined by U, it's equal to this kernel distance. Okay, the point of this is that if I know my whole point set ahead of time, I can construct a linear 2n dimensional space where everything acts linear. The kernel distance itself is a nonlinear thing, but this is a way of doing nonlinear analysis, turning it into a linear problem. And it includes that the distance I measure between 2 points becomes is the Euclidean distance in this space. And so there's a lot of other Euclidean stuff that happens. Okay, and so to really think about this is one perspective of the linearity. So if you only kind of got that, that'll be kind of a good start. There's something more complex, reproducing kernel Hilbert space. Okay, RKHS. Okay, and this is a space is a space of functions. Okay, and it's going to be all linear combinations of functions that look like this. Okay, so if I look at this kernel function where I'm only giving one argument for P, this is going to be an element of the space. Right? So if I have a kernel, that's a valid function, but so are linear combinations. So one common linear combination is called the kernel density estimate. The KDE of a point set P at a value, let's say, value X, that's going to be 1 over P of, I look at all the points in P and I average the effect of the kernel on a value X. And so in fact, the KDE of any of these point sets where I did not specify the argument is a function and it lives in this space as well. Okay, so this is a space of functions. Okay, it's a space of functions that acts like a linear space. For any finite, the linear combinations of any finite set of points, all the functions, all the weighted combinations, including with negative weights, all is in the space. And for if it's finite, then the space is linear. It acts just like Euclidean distance. Okay, and in fact, I can write the kernel distance between P and Q. It turns out is going to be equal to, in this space, if I look at the kernel density estimate of P, again, this is the function without the, compared to the kernel density estimate of a point set Q, and I look at the norm in the space, which I could get through this grand matrix and the orthogonalization of it, right? It's equal to this kernel density estimate. But the difference in the kernel density estimates in the space, I take all the points in the space, I take their average as 2 points, and I look at the Euclidean distance between their averages, and I can write this as the expected value of P from the point set P of the kernel. This is an element of the function space minus the expected value from the point set Q of Q in this function space. Okay, and the fact that it's comparing two means against each other is where the maximum mean discrepancy name comes from. Okay, but the point is, I basically turned these 2 point sets through a nonlinear process into an average of 2 things, and then I can look at the difference between those averages. So if I can get this representation, and there are fast, approximate ways to do it, then I can treat them as just taking the average between 2 kind of points in this high dimensional space. Okay, and this will mean that anytime we want to use these kernel methods, this kernel trick, where I'm replacing things with this kernel inner product instead, I can do that and treat it like Euclidean stuff, and all the algorithms we'll start talking about next week that can use Euclidean distances and metrics can use this in place as well. Okay, that was a very fast introduction to kernel methods the last 20 minutes. So, okay, we'll stop here.